Hello everybody, how are you? This lesson is about gravity. You are familiar with Newton's first three laws, and Newton's law of gravity is sometimes also referred to as his fourth law. And it just describes what are two objects doing with each other. Well, they attract. So it can be here the Earth maybe, and an apple, or whatever you want it to be. So any two objects having a mass, they will attract. So the forces here are always attracting. So we have a force towards this side, which is gravitational force 1. And we have a force on the other object, Fg2. So I have drawn these vectors exactly the same length, since we know Newton's third law, actio reactio, and it tells us if the green one is pulling the red one is pulling the green with the same force. This, of course, holds also true in this case. So gravity depends on the mass of the two objects. So we have here the mass of the one and the other object, m1 and m2. And also on the distance of these two objects, which is referred to as r. R, be careful, is always the distance from the center to the center of the object. So this here is going to be r. So it's a distance between the center of mass. And it is then the force proportional to the inverse of r squared. So we will have a look at a couple special cases concerning this gravitational force. And the most important application is 711. If we are close to the surface of the Earth. So gravity on the surface of the Earth. Okay, if you're astronomer, then this might not be the most important case, but for regular applications, this is by far the most common application of gravity. So we have learned now or seen this Newton's law of gravity, G times m1 m2 over r squared. And on the Earth, we have also in former lesson have seen that this can be written as m times g. And basically these two laws, same thing. So if we draw the situation, then we have on the one side the Earth given and an object, and the object is on the surface of the Earth, rather small usually. And we can therefore now find out what is r. Well, this is from the center of the Earth towards the center of the object, which roughly is the radius of the Earth plus a couple centimeters or meters or maybe a kilometer. And the rest is given. So we can see that g here has to be the same as that one, in case that I refer this m to be m1 here, the mass of the apple, for example. So we can quickly check if this is true. So g is given as g times, must be the mass of the Earth, divided by the radius of the Earth squared. So let's check this. G then is here. So check. This we can get the number here from above, 6.67 here times 10 to the minus 11 Newton meter squared over kilogram squared. Mass of the Earth 5.97 times 10 to the 24th kilogram, and the radius is some 6,370 kilometers, so we have to multiply times 10 to the power of 3 to get meters and take this to the square. And you will find out, if you put this into your calculation, that you just get these well-known 9.8 meters per second squared. This same idea also works for Mars, for example, if you take the mass of the Mars and the radius, or for Jupiter, or for any other object that you might have. This G value is not the same all over the planet. For example, if we go to the North or the South Pole, it's more or less the same. You measure a value of 9.83 meters per second square, while as if you go to the equator, you measure a value of 9.78 meter per second squared. So these values are really from a measurement from the free fall, as we have done in a former experiment in kinematics. And we can see that the difference here is roughly here 0.05 meter per second squared. And the question is now, where does this come from? One answer is, well, the Earth is not a complete sphere, so it is a little bit flattened, and therefore the distance from the center is different. And in fact, this is true. But there is also a second influence on this value. And this influence is rotation, the circular motion. So we will have a look at G and the rotation of the Earth. So again, I draw the Earth here with the axis, and it is turning here around the axis, and we can draw here the pole, the equator line, sorry, and we are maybe standing here, or we could also be standing up here. And now let's have a look at the centripetal acceleration here. First at the pole. Well, what is the radius that this top red point here is having from the axis of rotation? And the answer is 0, and therefore it is just simply 0. So no effect here on the pole. However, if we look here at the equator, it's going to be different. So we know it is here just r times omega squared, and we can have a look at that. So r 6.37 times 10 to the power of 6 meter, and for the rotation we take 1 turn, 2 pi within 24 hours times 3600 seconds to the power of 2. And if we put this into the calculator, we get a value of 0.034 meters per second squared. So we can roughly say that rotation is just half of the story, and the flattening is roughly the other half of it. So rotation does have an influence. Things, of course, will be getting a little bit more complicated if you go, for example, at a position up here, maybe in Iceland or so, if you are somewhere a little bit closer to this axis, and we will have an exercise having a look at that special issue. Or it could also be fun if the rotation of the Earth were quicker, then of course this centripetal acceleration gets larger and larger, and at some time you would not be really able to stand on the Earth anymore and just feel at least lighter and lighter. So we really have to distinguish what we are telling about or talking about, and there is two g values. We have one g value, which is the one that we have measured, for example, in an experiment using the free fall, and this is given by the g that we get out of gravity. So really from this Newton's law, and it is diminished by the amount of here this centripetal acceleration. So be careful in the exercises which g we are talking about.